Hello and welcome to our video key for our fourth exam in Calc 3, our Chapter 4 exam here. So I'm just going to dive right in. Our first question is a related rate question. You can see we have this triangle, and I'm going to label this, we'll call this Y. Oh, actually, hold on. Let me change pen colors. So we'll call this Y. You can call it maybe height, maybe H for height. Makes more sense. What do we know here? Terminal velocity of 122 miles per hour. So dH dt, the rate he's falling, that's actually negative 122 miles per hour because H is shrinking. How fast is the angle with the ground, theta in drawing? So we're trying to find d theta dt. How fast is it changing when the skydiver is 1 mile from landing? So H at that particular moment will be 1 mile. All right, we need an equation that relates these, and so I would just use tangent. Tangent theta equals h over 2, and I think we're ready. Let's differentiate both sides with respect to t. We have secant squared theta times d theta dt, and then on the right we have 1/2 and then dh dt. And so we are almost ready here. Let's see. Secant squared is 1 over cosine squared. So if we multiply both sides by cosine squared, we have this. Now we know dh dt, that's negative 122. We need to figure out cosine theta. So let's see, we have theta, we have 2 miles, 1 mile, and we could find the other side would be, let's see, 1 squared plus 2 squared equals the hypotenuse squared, c squared, whatever. So c is square root of 5. So I think we can do cosine now. 1/2 dH dt is negative 122, and then cosine will be cosine, why is it doing that? Is adjacent over hypotenuse, but then we have to square that. Let's see, half of negative 122 will be negative 61, 4 over square root of 5. Pull my calculator out here. Can't see what I'm doing because I'm not recording that, but that's okay. Negative 61 times 4 over the square root of 5. So I got about negative 109.1, and that is radians per hour. It's kind of a weird unit. The 122 was miles per hour, and then it's kind of a little confusing. The h here, when we took a derivative, dh dt, the h over 2, those were actually unitless, and it's a little confusing, but we lost the miles in the conversion, and there's no degrees here, it's just radians. Oh wait, hold on, that is, we forgot to square the, the square root of 5. So that gives us, let's see, what is that? The negative 48.8 radians per hour. Negative 48.8 radians per hour. I don't know if anybody watched this video. It's really funny. I'm not going to link it now. It was kind of fun, but I was also in a panic, and I ended up like super dizzy, and it was not good. All right, number 2, consider the function. We're going to find all critical numbers. So we need to find f prime of x and see where it is 0 and where it is undefined. I like to rewrite these. It's kind of weird italics there. I like to rewrite it as a power, so we'll use the chain rule, 1/3 times x squared minus 4 to the negative 2/3, then times 2x. So that gives us 2x over 3 times x squared minus 4 to the 2/3. All right, let's set that equal to 0. It's equal to 0 when the numerator is equal to 0, so that means x is 0. And then it's undefined, f prime of x does not exist when the denominator is equal to 0, and so that's at plus or minus 2. So we have 0, positive, or negative 2. So increasing, decreasing, we'll make our chart f prime, and we've got, nope, not 0, negative 2, 0, and 2. It's kind of nice here. We could go like negative 10, negative 1, 1, and 10, and we'll plug those in our derivative. Let me recopy that here. 2x over, now I'm going to cheat a little bit. x squared minus 4. Do you see the 2/3, right? This is really like 2x over 3 times the cube root of x squared minus 4 squared. So you see that denominator is always going to be positive. So the only thing that changes the sign is the numerator. Super sneaky cheat there. So 2 times negative 10, that's negative, decreasing. 2 times negative 1, that's negative, also decreasing. 2 times 1, positive, increasing. And 2 times 10, positive, increasing. So f is decreasing on the interval. Now let's see. Oh, that's an f prime. What is the original function? Is that an asymptote there, or is that a cusp? Let's see here. It looks like there's no asymptotes. It's a cube root. So that's just maybe a cusp or a vertical tangent line. If it's decreasing before and decreasing after, probably a vertical tangent line. So I'm going to say, but it's still decreasing. So negative infinity up to 0, and then increasing, and the same thing, 0 to infinity. And we could double check. I've got a Desmos window up here. Let's type y equals cube root of x squared minus 4. Oh yeah, okay, makes sense. All right, we've got decreasing, still decreasing, and then increasing and increasing. Yeah, nice. Okay, back over here. All right, absolute maximum, absolute minimum value of the function on the indicated interval. All right, well, we need to find critical numbers. 12x cubed minus 12x squared. And we're going to set that equal to 0. So 12x squared times x minus 1 is equal to 0. So you have x equals 0 and x equals 1. Well, 0 is an endpoint already. All right, so let's test f of 0. That's 0. F of 1, 3 times 1 to the 4th minus 4 times 1 cubed. 3 minus 4, that's negative 1. And then f of 2, 3 times 2 to the 4th minus 4 times 2 cubed. 3 times 8 is 24. 8 is 32, so that's negative. Is that negative 8? So it looks like absolute max will be here. And absolute min here. Interesting. I think I want to graph this one too. Absolute minimum is 0 when x equals 0, and absolute maximum, no, that's the absolute max. Absolute minimum is negative 8 when x equals 2. Let's just do a quick double check on that one as well. F of x equals x to the 4, no, was it? 3x to the 4th plus 4x cubed plus 4 or minus? I think it was minus. Double check. Oh, looks like I have a problem here. Minus 12x cubed minus 12x squared, x equals 1. 2. Oh, 2 to the... See, this is how I knew it can't be negative 8, because that's why you use the graph, right? At 2, it's way up high. That doesn't make sense. So that was because I am not good with arithmetic, apparently. Okay, so 2 to the 4th is 16. 16, not 8. 3 times 16 is 48. And so we get 16. So the absolute maximum is 16 when x is 2, and the absolute minimum is now negative 1 when x is 1. Nice. That's all right, we caught it. All right, number 4, we're going to find the intervals where f is decreasing and increasing. Well, we already have the critical numbers. This is the same function we just did. There's 0 and 1. So let's check negative 10, 1/2, and 10. F prime of x was 12x squared times x minus 1. F prime of negative 10 will be 12 times negative 10. Well, that's squared, so it's always going to be positive. So negative 10 minus 1 will be negative, decreasing. F prime at 1/2 12 times 1/2 squared times 1/2 minus 1, still negative there. And then f prime at 10 will be 12 times 10 squared times 10 minus 1. That's positive increasing. So f is decreasing on the interval -infinity to 1 and increasing on the interval from 1 to infinity. Okay, relative extrema looks like f has a relative minimum at x equal to 1. And in fact, the point was, didn't we do this one already? 1, -1, right? Okay, concave upward, concave downward. We need to take derivative again. F prime of x was 12x cubed minus 12x squared. So the second derivative will be 36x squared minus 24x. Let's double check that I've got derivative right. Yeah. Okay, we can factor out, what can we factor out there? 12x. All right, 3x minus 2, and so we get x is equal to 0, and x is equal to 2/3. Let's make a second derivative chart, 0 and 2/3. Let's check maybe -1, 1/2, and 1. And let's see here, we've got 12x times 3x minus 2. So let's see here, at -1, f double prime at -1, 12 times -1, 3 times -1 minus 2, that's negative, negative. The whole thing will be positive, concave up. F double prime at 1/2, 12 times 1/2, 3 times 1/2 minus 2, positive, negative. It's concave down. And then f double prime at 1, 12 times 1, 3 times 1 minus 2, everything there is positive, concave upward. So f is concave upward on -infinity to 0 and 2/3 to infinity. And then f is concave downward on the interval 0 to 2/3. Okay, find any inflection points. It does look like we have inflection points at 0, and that one's 0, 0. And then, 2/3. Yeah, f of 2/3 equals, what was it, 3 times 2/3 to the 4th minus 4 times 2/3 cubed. Can we cheat with that? I think I could type that in here. 3 times 2/3. Oh, I don't think it can do fractions though, to the 4th. Huh? Yeah. Minus 4 times 2/3 cubed. Yeah. Nice. Decimals for the rescue. -16/27. -16/27. So those are the two inflection points. Okay, moving right along. We have this graph. We're going to use the graph to estimate the date for the inflection point. Using calculus vocabulary, explain why this is the inflection point, and then suppose you had to explain the meaning to someone you know. So I'm going to do some of that verbally because I don't want the video to take longer. Just watch me while I'm writing. So inflection point is when the concavity changes. You can see it happens. It's definitely concave down here. It's definitely concave up here. So somewhere in here, maybe like right here or right here, something like that. It's kind of hard to tell. I mean, I'll accept any answer in there. Let me open up this link. I can't open up the link. It's not live in here. So let's call it, we'll call it right in the middle. I don't know. So we'll say something like March 2nd maybe. So for the calculus reason, it's essentially because it changes from concave up to concave down, right? It's a change in concavity. Now, if you're going to try to explain that to someone else, a change in concavity is not going to make any sense. They don't even know what concavity means. So the key there is that's when the rate of change changes. You see how they're getting more and more and more and more cases per day. So the case per day is increasing, but then the cases per day starts decreasing. So this is the point where the new cases per day, the rate of change is maximum. The new cases per day is maximum. So that's a maximum for the rate of change. That's the key about that day. So how I'm going to grade this, I don't know, I haven't done the grading yet, so I'm not sure exactly how that'll work. So we'll see on that. But I'm looking for something about the rate of change is maximum. So I'm going to be pretty liberal on the grading there. It's a tough one to describe. Okay, silly comic here, mean value theorem. The key for the mean value theorem is you have this secant line, and look here, the slope is equal. So f prime at C is equal to the slope between the endpoints, f at B minus f at A over B minus A. So that's the key there. I think is this the last one? Oh, we have more. Some antiderivatives, right? So this is actually true that this is how you make maple syrup. I make maple syrup, in fact. We have a little pan that's kind of fun. We tap some trees in our yard. We want to construct a sealant pan. The surface area on the bottom of the pan is 576 inches. So that means x times y equals 576 square inches. We got a height of 6 inches. You want the pan to cost as little as possible. If food grade stainless steel costs 50 cents per square inch, what dimensions should the cost be, or should the pan be to minimize cost? So cost is 50 cents. It's really going to be 50 cents times the area, the total surface area. So that's 50 cents, 50 cents times, we have xy on the bottom. The top is open. We have 6 times y, but 2 of those for this side and then the other side. And then we have 6 times x, but then 2 of those as well. So it looks like our cost is, I'm going to just call it 1/2 xy, and then 6y and 6x after we distribute the 1/2 here. That's a function of x and y, though we need a function of just one of them. So if we use our fact up here, we can say y is 576 divided by x. So then my cost now as a function of x will be 1/2 x times 576 over x plus 6 times 576 over x plus 6x. Let's see here, half of 576 over 2, 288. So this is just, and we lose the x. That's just 288 plus, then we need 576 minus 6, 3456 over x plus 6x. Now that's cost as a function of just x. So we want to minimize it. Let's take the derivative. We will lose the 288. We'll get negative 3456 over x squared. I'm doing that because I'm treating this as 3456 times x to the negative first. And then plus 6. We want to set that equal to 0. So we get 6 equals 3456 over x squared. We can multiply by x squared. 3456 equals 6x squared, divided by 6, x squared equals, we get our 576 back. And so then x will be the square root of 576. Let's see, the square root of 576 is, it's 24. X is 24. Now normally we do plus or minus, but we're looking at dimensions. So we can't do plus or minus. Y will be, it was 576 over 24, and that's 24 also. So the pan really should be 2 feet square. The pan should be 24 inches by 24 inches by 6 inches. All right, now we have some antiderivatives to finish it up. Finding the antiderivative here, this will be We'll call it capital F of x, the antiderivative. It'll be e to the x, right? Because the derivative of e to the x is e to the x. And now we're going to use our reverse power rule. We're going to add 1 to the exponent and then divide by that new exponent. And you can always check by taking the derivative, you would multiply and just get 1x squared. Here we will have tangent theta, right, because the derivative of tangent is secant squared, and then plus cosine theta, because the derivative of cosine is negative sine. Last one here, we're going to do an antiderivative, almost at f of x, it's f of t. We're going to do, let's see, 8, and then we'll have t to the 4th divided by 4, and then 5t plus some constant. So f of t will be 2t to the 4th plus 5t plus c. And then we know that f of 1 is negative 4, so f of 1 will be 2 times 1 to the 4th plus 5 times 1 plus c, and that should be negative 4. So 2 plus 5 plus c is negative 4, 7 plus c is negative 4, and so c is equal to negative 11. So we have our f of t now. It is 2t to the 4th plus 5t minus 11. Okay, kind of a long video. That is it for this one though. Let me know if you have any questions. Shoot me an email. We can have some discussion in class as well, and we'll use this for our usual reflection.